it. But almost 14-15 years are over by doing this, and now everybody is aware of this technology. Most of people are aware of this technology, and we are entering into an operational class of remote sensing satellites. And with the experienced people from ISRO is supporting this, we thought we should transfer from amateur level to a professional level of satellite building. So we have configured a satellite for disaster management application, an operational type of payload with around 20 to 30 meter resolution and about 60 to 100 kilometers square, which are equivalent to the first IRS satellite. List 2 was providing that type of imageries. Even now there is a List 2 demand is there from various user community, and is not met by ISRO because of the non-availability of List 2 data. So we are now trying to fill the gap for building a nano satellite, accommodate a similar payload. So with that concept, we have gone for a nano satellite called the NIU SAT. It was a totally university funded satellite at the Nurul Islam University in Nagarkoil. It is a very remote area in the southern regions of Tamil Nadu. I just wanted to highlight some of the features of the satellite. So this satellite is actually a nano satellite designed and developed in the university with using a wide field sensor, miniature wide field sensor. Actually, WIPS was used in the IRS satellite. It's a miniature version of that, less than 1 kilogram payload for agriculture and disaster management applications. Mainly, we have seen the diseases, how the diseases are spreading in that area was not detected. Okay, all other satellites providing support for the healthiness of the plant or the growth prediction is there. But how the diseases are spreading, it is not yet analyzed. And we are now targeted for once this satellite is launched and the images are available, it's possible to predict the diseases. Mainly that area was plantain, the Nagarkoil region. The plantain, paddy and rubber trees are extensively grown in that area. So there are some diseases spreading, and coconut trees are also there. Some like root wilt disease which was spreading in the coastal regions of Kerala. This particular data can provide support for analyzing how the diseases are spreading in particular regions, so we can take protective action to prevent the disease spreading. So that was the target. In addition, these imageries will be useful for identifying the landslide, flood. So we have selected the bandwidth such that, the spectrum such that it is possible to detect the flooding and the landslides and the forest fire. So that type of applications are possible. So this is actually a totally university program involving almost 120 students are involved in that, and many subsystems are getting realized. I just show you some of the features of the satellite. So mainly, of course, any satellite program, we should have a mission idea. So the overall mission comes under that. We have the mission definition. Okay, what exactly you wanted to do. Mission definition involves the mission concepts and the mission requirements, what exactly required for as a satellite, launch vehicle, ground station. So the mission requirements and the mission operations. How are you going to do as a satellite is built, and how are you going to operationalize the satellite, and how are you going to use this data for application purposes. And it has to interface with the launch vehicle. What are the environment, the launch vehicle, what is the type of launch vehicle we are going to, we are going to use the PSLV launch vehicle. What is the launch vehicle environment, how the satellite has to withstand the environment of the launch vehicle with respect to vibration, shock, acceleration, all these things. And the whole satellite itself is one element in the mission. The space system itself, it has an onboard computer, telemetry, telecommand system, structure, mechanisms, and the payload itself, plus the attitude and orbit control system, electrical power system, etc., and all to be integrated into the satellite. And the ground system, afterwards the satellite, once it is launched, it has to be, data has to be received, it should be processed, and we have to give a meaningful product to the user agencies. So that type of things also is planning. And overall satellite assembly, integration, and ground checkout. See, but before launching the satellite, whole thing has to be reproduced here. So entire process has to be reproduced here, and it should be checked to all the environment levels, so that after launching, if the satellite will be perfectly operating in the orbital environment. So that concept has been put in the scenery of the university environment, and almost 10 professors have been identified, because the satellite is a multidisciplinary activity. It involves the mechanisms, involves the structure, thermal, control systems, electronics, avionics, all the things are involved. So, and the overall ground system also is involved. It is a totally complex multidisciplinary activity, and almost 10 departments are working together to realize this satellite. So this is the overall configuration of the NAU set. You can see it is actually the structure is 274 by 274 by 195. I have learned a lot of things during our ISRO, working with ISRO. We have the IRS bus was actually configured in 70s and 80s. Almost 20 satellites were built with the bus actually. Now I don't think any other bus has that many satellites built. Various types of payloads, whether the ocean sat or the metsat or meteorological satellite, all are built on the bus. What we have seen conceptually, the bus should have two elements, two portions or the two modules. There are mainframe systems which supports the operation of the satellite. That is like structure, telemetry, telecommand, attitude and orbit control systems, thermal control systems, the power systems. All are, and it should be accommodated. It should support the whole payload on top of it. And the payload, any type of payload, it should be possible to accommodate. So the same concept we have adopted here. And it was actually miniaturized version of an IRS type of satellite. The thermal is one of the important aspects. So all the subsystems which are dissipating power are accommodated on the side panels. The common subsystems which are attitude and orbit control system, onboard computer, telemetry, telecommand system, which are common for all the subsystems are accommodated in the center bay. And all other power system, propulsion system, transmitting system, our communication system, all are accommodated on the side panels. And the top deck is free for accommodating any type of payload. So you can see we have 2-3 configurations itself. So the payloads on top of it, we are now accommodating a nano cam, which was developed by ISRO's Space Applications in Ahmedabad. It has a 4-band camera. We are modifying it to 3-band camera for this application. And it can accommodate star sensor on top of it. And we have all other sensors, sun sensors, magnetometers, gyroscopes, all are accommodated on top deck, which has to be mounted very close to the payload, because that is the one defining the axis of the whole satellite. Rest of the subsystems, I will show a bit more detail. So the structure is of almost, this comes to around 14 kg right now. We have targeted it should be less than 15 kilograms. And the structure weight itself roughly around 3.8 kg. And the solar panels are actually, and one more limitation what we have seen in the conventional CubeSats are the body mounted solar panels. The power was one of the constraints, not able to provide power requirement of the many payloads. So we have configured deployable solar panels, 4 deployable solar panels attached to the side panels, so that we can anytime, immediately after launch, we can deploy the solar panels, adequate, almost 40 watts of power it can generate. So 100 kg satellite presently IMS-1 is able to generate 40 watt. Similar capability we are able to generate using 15 kilogram satellite. So the payload itself was actually the wide field sensor, which was actually 4-band. They have the capability for 4-band, and resolution will be of the order of around 35 meters at around 600 kilometer altitude, and the swath is 140 kilometers. Of course, the quantization, of course, they are all declared with respect to quantization. All these things are almost similar to the WIPS camera, what is already in the orbit. The mission itself, we are trying to put it along with this PSLV launch vehicle, will be around 500 to 600 kilometer altitude, and the inclination will be a polar sun-synchronous orbit equivalent to for Earth imaging. Throughout, it can be used for any global imaging purposes, not only our own region. Because of we are making use of the precision of the orbit and the Earth's rotation. We can give global coverage. So not only to our region, anywhere in the globe we can image in every day. And with respect to the attitude and orbit control system, we have the sun sensors, magnetometers, MEMS gyroscopes, to provide the 3-axis attitude determination as well as attitude control. For control purpose, we are using the magnetic torquer and the micro reaction wheel. We are jointly developing through Sona College Engineering, where one of our experts is working as a professor in the college. And the control algorithm is developed, implemented on an onboard computer. And the onboard computer itself, we are actually developing a high power computer. What we have seen, the ARM and the big processors are used in many of the nano satellites. We wanted to have a smart satellite actually. So many onboard processing, even the payload data, we would like to process it onboard so that the ratioing of the bands as well as the radiometric compensation as well as the geometric compensations are possible on board. So only the minimal data or the changes only will be transmitted. That way the data transmission load will be brought down. So we wanted to have a powerful onboard computer using a power PC based onboard computer we are just developing. And the power system itself it can generate almost 40 watts. And around nominally we have actually a redundant bus. We have seen many satellites in the operational satellite, the failures were 50%, more than 50% were the power system failures. We take even Jimnu, we have the, even first IRS, our Aribata satellite, we had the power problem. So even after learning, we have seen the failures were occurring because of the power system failure. We are having a redundant bus actually. So it is 20 watt, one bus can provide. And a single bus, we are able to meet the total mission requirement. Only the operational duration, payload operational duration, we can bring it down. And see, around 15 watt will be consumed for the mainframe, almost 10 watt for the payload. So around 25 watt, we are able to cover the total requirement for the power. We have adequate margin available for charging the battery as well as even one bus failure, we are able to do the full mission support. The communication will be with the UHF, VHF. UHF will be the downward transmission and the VHF will be the uplink. And we have option to go for S-band as well as UHF antenna for UHF communication for payload data transmission. Normally we have seen emergency communication, the real time we have to get the payload data. It will be at the rate of 1 megabits per second using S-band. In normal cases, we can go with the UHF with around 40 kilobits per second. So one frame of 60 kilometer by 60 kilometer we can transmit per day using UHF. And if we go real time, we have many frames we can transmit through the S-band. So that option we are kept here. So and also we are establishing a ground station, the full-fledged ground station for UHF and VHF antennas, and a 3-meter reflector S-band antenna. And we have an integrated mission control center, ground checkout system, and the antenna tracking system established there. So there's an integration topology. The development of, normally the different things are developed. The mission will be developing independently, the mission operation sequences, and the checkout system will be developing their own software. Now it's an integrated software development for checking the satellite onwards. The same software will be used up to the mission operation. So that way the developmental effort required will be less in this.